a rigorous method for identifying a one-dimensional reaction coordinate in complex molecules. Shanshan Wu, Huiyu Li, and Alma cite this. J. Chim. Theory Compute. 2022, 18, 2836-2844. Read online. Access metrics and more article recommendations. Abstract. Understanding the mechanism of functional protein dynamics is critical to understanding protein functions. Reaction coordinate, RC, is a central topic in protein dynamics, and the grail is to find the one-dimensional RC, 1D RC, that can fully determine the value of a committor, i.e., the reaction probability in configuration space for any protein configuration. We present a new method that, for the first time, uses a fundamental mechanical operator, the generalized work functional, to identify the rigorous 1D RC in complex molecules. For a prototypical biomolecular isomerization reaction, the 1D RC identified by the current method can determine the committor with an accuracy far exceeding what was achieved by previous methods. This method only requires modest computational cost and can be readily applied to large molecules. Most importantly, the generalized work functional is the physical determinant of the collectivity in functional protein dynamics and provides a tentative roadmap that connects the structure of a protein to its function. Proteins are the building blocks of biological systems responsible for most biological functions. Understanding the mechanism of protein function is of paramount importance. The central dogma of protein science is that structure determines function. The Holy Grail is the physical principle that explains how the structure of a protein determines its function. The route to this principle starts with recognizing that most protein functions, such as ligand binding, allostery, and effects of mutations, involve significant conformational dynamics because a protein has multiple functional structures and transitions between these structures are required for its function. 1,2 structure determines function because the specific structure enables the desired functional dynamics. Understanding protein function requires understanding functional dynamics. Importance of reaction coordinates. Most functional dynamics are activated processes similar to chemical reactions. A protein must cross an activation barrier much higher than thermal energy to move from the reactant, initial, state to the product, final, state. A central concept here is the reaction coordinates, RCs, the small number of essential coordinates that fully determine the progress of a reaction. 3. In particular, RCs determine the location of the transition state. The reaction progresses in the forward direction when RCs move toward the product state. It regresses when RCs move toward the reactant state. Movements of all the other coordinates are irrelevant. RCs are the cornerstone of the standard reaction rate theories. Reaction dynamics is the dynamics of RCs. Indeed, Kramer's theory assumes that the dynamics of the RC is governed by a Langevin equation, which is extended to the generalized Langevin equation in Groth-Heinz theory. 5. Similarly, transition state theory relies on simplifying assumptions on the essential features of the dynamics of the RC. 6-10. The applicability of all these theories requires full knowledge of the RCs. RCs are also central to enhanced sampling, a major current research direction in computational biophysics. Most algorithms rely on applying biasing potentials on one or a few collective variables, CVs, selected by intuitions to increase the sampling of the relevant configuration space. 11-17. However, these algorithms are effective only if the CVs coincide with RCs. Otherwise, the infamous hidden barrier problem will inevitably appear and prevent effective sampling. 18-20. The hidden barrier is the actual activation barrier that lies on the true RCs, which is missed by the biasing potentials along CVs that do not overlap with the RCs significantly. Rigorous concept of RCS. Given the central importance of RCs, a rigorous definition is essential. An important concept is the committor, PB, the probability that a dynamic trajectory initiated from a system configuration, with initial momenta drawn from Boltzmann distribution, to reach the product state. 3-21-23. The committor rigorously parameterizes the progress of a reaction. For example, the transition state has PB equals 0.5. Consequently, RCs are the set of coordinates that can fully determine the committor value of any system configuration. Other coordinates in the system are irrelevant. RCs that satisfy this definition provide an accurate reduced description of a reaction. In contrast, ad hoc RCs that do not satisfy this definition bear little relevance to reaction dynamics and mechanism. 24,25. A critical question is how many RCs are there in a system? The standard reaction rate theories assume that, for a single-channel reaction, there exists a single one-dimensional RC, 1D RC, that can fully determine a committor. Even though the multidimensional extensions of these theories assume that a reaction is controlled by the free energy surface of multiple RCs. It is assumed that there is only one unstable direction in the saddle region, 7,26, which is the direction of the 1D RC. The seminal work by Barashkovsky and Szabo 27 showed that it is possible to find a 1D RC that reproduces the same reaction rate determined by multiple RC'(S. 28,29. For single-channel reactions, the concept of multiple RCs is an approximation to the concept of 1D RC. In the schematic example of Figure 1a, Q1 and Q2 are considered RCs because they both have significant overlaps with RC, the 1D RC. However, they also have components orthogonal to RC, pointing to their inaccuracy as RCs. The concept of multiple RCs is semi-quantitative and has some leeway. The concept of 1D RC is quantitative and precise. The former is adopted much more widely 3,30 because, compared to the 1D RC, they are much easier to identify. Goal for studying RCS. The rigorously defined RCs offer a chance to bring order to the apparent chaos and complexity of protein dynamics that thwarted understanding of the protein function. The small number of RCs compared to the myriad of coordinates in a protein indicates that protein dynamics has an intrinsic order and governing principles, which is embedded in the RCs as they accurately describe the progress of protein dynamics. The physical cause behind the RCs is the physical determinant of this intrinsic order. The goal for studying RCs is to uncover and, furthermore, understand the principle behind this physical determinant. Challenges in identifying RCS. The first step toward this goal is to identify the less strictly defined multiple RCs since it is easier than identifying the 1D RC. However, it turned out to be a daunting challenge. Despite much efforts, over the past 2 decades, there have been only a few successful cases where RCs that can determine the committor were identified. 30-33 in each case, 2 or 3 RCs were successfully identified. The most important lesson from these examples is that RCs are often counterintuitive. 30-31. This counterintuitiveness demonstrates why it is challenging to identify the few RCs out of practically infinitely many potential candidates in a complex molecule. For example, over 6,000 candidates were tested in Ref 31 for the C7eq alpha R isomerization of an alanine dipeptide in solution to uncover the 3 RCs. As a result, systematic methods that go beyond intuition-based trial-and-error experimentation are required as it is not feasible to enumerate the enormous number of potential candidates. The Dolk-Stacevitbold by Motu Payne. First systematic method used a neural network and successfully identified the RCs for the C7eq alpha R isomerization of an alanine dipeptide in solution that eluded human intuitions. 31. This early success is followed by many machine learning methods along similar lines, a research direction that is currently attracting intensive attention but also facing significant challenges. 25,34-38 More importantly, machine learning methods cannot answer the question central to the goal of studying RCs. Why do RCs exist and how do they control functional dynamics? Answering this question requires the correct mechanical model of functional dynamics, which machine learning cannot provide because it can only optimize parameters based on a pre-formulated model but cannot construct a model de novo. An approach based on fundamental physics is required. Figure 1. 1D RC and structure minus function relationship. A. Schematic of the potential energy surface in RCs of a two-dimensional system. The light yellow region indicates the contours of the potential energy surface, with the reactant and product states marked by R and P, respectively. The green dashed rectangle marks the transition region. The orange curve RC indicates the 1D RC and the blue line segments RC is its piecewise linear approximation. B. Flowchart for the tentative roadmap for the physical principle that connects the structure of a protein with its function. Physics-based approach for understanding RCS. The recently developed energy flow theory offered some insights into the physical principle behind RC'(S.32,39). It showed that energy flows from the fast to the slow coordinates during a reaction. 32. Because RCs are the slowest, they carry the highest energy flows. This picture is intuitively appealing and explains why RCs are very important. Energy is the currency of dynamics, and movements of RCs incur the highest cost. Thus, they control reaction dynamics by dictating the overall cost. However, this picture is still semi-quantitative and does not answer a critical question. What is the relationship between different RCs? This question is automatically answered if we can identify the 1D RC, because it is a function of the multiple RCs, which defines the precise relationship between them. Moreover, 1-3 answers a key conceptual question. What is the physical origin of collectivity in functional dynamics? It is generally assumed that functional dynamics are controlled by one or a few CVs, the reason being that CVs are widely used in enhanced sampling. However, the critical questions have never been answered. Why functional dynamics are collective and what determined the CVs? By definition, 1D RC is the optimal CV. Thus, the physical determinant of 1D RC is the physical origin of collectivity in functional dynamics. In this paper, we introduced a fundamental mechanical operator rooted in Newton's law, the generalized work functional, GWF, which determines the correct 1D RC. Applying this new approach to a prototypical biomolecular isomerization process, the C7EQ, C7-AX transition of an alanine dipeptide in vacuum, we obtain, as an accurate approximation, the piecewise linearization of the 1D RC, for example, RC in the example of Figure 1a, throughout the entire transition. Region, i.e., PB element, 0, 1. Each linear segment is a combination of 4 component RCs, 2 dihedrals and 2 improper dihedrals. This 1D RC can predict the committor value throughout the entire range of PB with an accuracy that approaches the limit of the numerically evaluated committor values. This accuracy far exceeds what was achieved by previous methods. 30, 31. Among the 4 component RCs, the 2 improper dihedrals were only identified by the current method. Their inclusion significantly improved the accuracy in predicting the committor value. Most importantly, the GWF is a generic physical property universal to all protein molecules, allowing us to answer fundamental questions concerning RCs and functional protein dynamics. 1. Why do RCs exist and how do they control protein dynamics? 2. What is the relationship between different RCs? 3. What is the origin of collectivity in protein dynamics? The GWF summarizes the mechanical effects of the couplings between different coordinates. It shows that, due to the special structural features of a protein, a small number of essential forces have high impacts on the dynamics of the entire system, while the other forces have only minor effects. The directions of these essential forces are the RCs. Motions of RCs control these essential forces, thus RCs control the reaction dynamics. The GWF is a tensor. Its inherent structure can be revealed by singular value decomposition, SVD. The leading singular vector from SVD identifies the single dominant force. Its direction is the 1D RC, which is a function of all the RCs. The motion of 1D RC is a synergized motion of all the RCs. This synergy is the origin of collectivity in functional dynamics, as the dynamics of RCs is the crux of protein dynamics. From these results emerges a tentative roadmap that connects the structure of a protein to its function. Figure 1b. Protein structure determines both atom-atom interactions and the structural coupling tensor responsible for the mechanical couplings between different coordinates. Together, they determine the GWF, which determines the directions of the strong forces that appear as the RCs. Finally, RCs control the functional dynamics, which determines function. In this roadmap, the GWF plays a pivotal role. It is the underlying mechanical structure that determines the behaviors of the geometric structure we observe. Results. Energy flow theory. A major theoretical tool we use for analyzing reaction dynamics is the energy flow theory. 32,39. It was motivated by a simple physical intuition. Motions of the most important coordinates in a dynamic process require high energy cost. In the Lagrange minus Hamiltonian formulation of classical mechanics, energy is the cost function of motion. If the motion of a coordinate requires high energy cost, then it has a slow time scale and controls the rate of a reaction process. To identify these important coordinates, we need a rigorous definition of the energy cost of the motion of a coordinate. This is challenging because the energy function of a system is dominated by complex coupling terms between different coordinates. There is no well-defined energy per coordinate. Therefore, we can only find the energy cost of the motion of a coordinate by projection. This is achieved through integration over partial differentials. The total differential of a multivariable function f of x1, 2, xn is df equals sum from I equals 1 to n of dx sub I partial of f in x sub I. Thus each partial differential, partial of f on x sub I of dx sub I, is the exact contribution of the change in x sub I to the total change in f of x sub 1, 2, x sub n. The coupling terms in f of x sub 1, 2, x sub n are precisely partitioned among all the variables through partial derivatives, partial of f on x sub I. Consequently, integral of partial of f on x sub I of dx sub I rigorously defines the contribution to the accumulated change in fx sub 1, 2, x sub n from changes in x sub I. Applying this idea to the potential energy of the system, we define the potential energy flow through a coordinate q sub I as the work on q sub I: 32. Delta W of t sub 1, t sub 2 equals integral from q sub I of t sub 1 to q sub I of t sub 2 of partial of uq vector on q sub I of dq sub I. Equation 1, where u of q vector is the potential energy of the system and q vector is the position vector of the system in the configuration space. According to equation 1, delta W sub I of t sub 1, t sub 2 is the change in u of q vector caused by the motion of q sub I alone along the dynamic trajectory in the time interval t sub 1, t sub 2. It is a projection of the change in the total potential energy onto the motion of q sub I and a measure of its cost. Kinetic energy flow is not used in the current analysis and is not discussed here. 39. To gain mechanistic insights, we need to look at how a mechanical quantity A of gamma, for example, potential energy flow, changes as a reaction progresses. We first project A of gamma onto a quantity, xi of gamma, that parameterizes the progress of a reaction, which we call the projector, and then average over the ensemble of reactive trajectories. Bra delta A of psi star, ket, equals integral of d gamma, rho of gamma, delta, A of psi of gamma, z of gamma, plus dzc, delta of z psi of gamma, z star integral of d gamma, bra delta A of psi 1 arrow, psi 2, ket equals integral from psi 1 to psi 2 of bra delta A of psi, ket. 2 here, rho of gamma, d gamma is the probability of finding the system in an infinitesimal volume d gamma around a phase space point gamma in the reactive trajectory ensemble. Delta of x is the Dirac delta function. Delta A of c of gamma plus dc is the change in I in a differential interval. Z of gamma plus dz, delta A of z1, z psi 2 is the change in A in a finite interval. z1, z psi 2, delta A can be delta W sub I. 32, 39. The ensemble of reactive trajectories consists of trajectories that cover the transition period of a reaction process but exclude the waiting period. 3. Generalized work functional. The source of complexity of protein dynamics is the highly entangled mechanical couplings between different coordinates. The potential energy flow through a coordinate QI provides an exact account of the energetic cost of its motion but does not account for the effects of the mechanical couplings between different coordinates. These mechanical couplings are a consequence of the mathematical structure of Lagrange's equation. The Lagrange's equation for a generalized coordinate Q sub I is derivative in T of partial of L on Q sub I equals partial of L on Q sub I, where L is the system Lagrangian L equals K minus U, defined as the difference between the kinetic energy. K equals sum on J, K equals 1 to N of double struct S sub I, JQ dot sub JQ dot sub K tensor 1 over 2. And the potential energy U here, double struct S, is the structural coupling tensor. Double struct S equals sum on alpha equals 1 to N of M sub alpha partial of X sub alpha on Q sub I partial X sub alpha on Q sub K, where the sum is over all the N coordinates in the system. M sub alpha and X sub alpha are the mass and a Cartesian coordinate of atom alpha. After expanding all the terms, we obtain F sub I equals partial of U on Q sub I equals sum on K equals 1 to N of double struct S dot sub I, KQ dot sub K plus fancy S sub I, KQ double dot sub K, plus 1 over 2 sum J, K equals 1 to N partial of double struct S sub J, K on Q sub I of Q dot sub J Q dot sub K. Equation 3. On the left-hand side is the force induced by dQ sub I, the infinitesimal movement of Q sub I. The right-hand side involves the velocities, Qk dot sub K, when K element, 1, N, and accelerations, Qk double dot sub K, of all the coordinates in the system. This means phi directly affects the movements of all the coordinates in the system. The effects of F sub I on Q sub K and the effects of F sub K on Q sub I are determined by the values of double struct S sub I, K and fancy S dot sub I K, which are determined by the time-dependent system configuration. In contrast, the Lagrange's equation for a Cartesian coordinate X sub alpha is the same as the Newton's equation. F sub alpha equals M sub alpha, X double dot sub alpha. F sub alpha directly affects only the motion of X sub alpha, not any other coordinate. This is because equals double struct S sub alpha, beta equals M sub alpha, delta sub alpha, beta, in Cartesian coordinates, where delta sub alpha, beta is the Kronecker delta, because F sub I directly affects motions of all coordinates. It is important to have a measure of the impact of F sub I on the motion of Q sub J where J does not equal I. One choice is bra F sub I dQ sub J ket where I does not equal J. Bra middle dot middle dot middle dot ket is the average over the reactive trajectory ensemble. The physical motivation is that if F sub I strongly affects the motion of Q sub J, bra F sub I dQ sub K should have a high value. Otherwise, it will be small. Accordingly, we define the generalized work of F sub I on Q sub J as double struct W sub I, J of xi 0 arrow, xi 1 equals integral from xi 0, xi 1 of bra F sub I of psi dQ sub J of xi. Equation 4. Which accumulates the impact of F sub I on the motion of Q sub K as the reaction progresses from psi 0 to psi 1. The collection of all the double struct W sub I, J of psi, is a tensorial functional fancy W psi in the configuration space, which we call the GWF because F sub I dQ sub J where I does not equal J is a generalization of the concept of mechanical work. For a specific value, Z1, double struct W of Z psi is a tensor fancy W Z psi from Z0 to Z1, which we call the generalized work tensor. With this definition, double struct W of Ci summarizes the accumulated effects of the pairwise mechanical couplings between different coordinates as a function of the progress of a reaction. Because double struct W sub I, J does not equal fancy W sub J, I. SVD is the proper tool to extract its inherent structure. Double struct W of xi from xi0 to xi1 equals sum from I equals 0 to n1 of sigma I ui vector sub I dot vi vector sub I transpose, where sigma sub I is the ith singular value, ui vector sub I is the ith left singular vector, and vi vector sub it transpose is the transpose of the ith right singular vector. The leading term in this decomposition, sigma sub 0 u0 vector sub 0 middle dot v0 vector sub 0 t transpose, is the dominant component of double struct W of C from C0 to C1. Accordingly, double struct F vec sub 0 equals partial of U on U vec 0 is the force in the direction of U0 vec sub 0. This force has the largest overall effects on the motions of individual coordinates in the system, because the 1D RC is generally considered the driving force of a reaction process. 3. It is intuitively enticing to contemplate that it may coincide with U0 vec sub 0. If this is the case, we have also found in GWF the physical determinant of the 1D RC. Example of biomolecular conformational change. To test if the GWF can determine the 1D RC, we applied it to the C7EQ to C7-AX isomerization of an alanine dipeptide in vacuum. This process is a prototype of conformational dynamics of proteins because alanine dipeptide is the smallest example of complex molecules. Here, we define a complex molecule as the molecule whose non-RCs form a heat bath that can provide the RCs with enough energy to cross the activation barrier. 3, 21, 27, 31, 32, 37. In contrast, small molecules need an external energy source, such as buffer gas in the gas phase and solvents in solution phase reactions. The isomerization of an alanine dipeptide in vacuum carries some fundamental features that are unique to reactions in protein-like molecules but are absent in small molecules. Consequently, it has served as a standard system for testing methods for identifying RC'(S.3, 30, 31. This isomerization process is mainly a rotation around the phi dihedral, figure 2a-b, in previous studies. 2 backbone dihedrals phi and theta1 were identified as the RCs as they can determine the committor value with adequate accuracy. 30, 31. Figure 2. Schematics for the C7EQ, C7-AX isomerization of the alanine dipeptide. A. Molecular structure of the alanine dipeptide. For a dihedral, its bond of rotation is marked by a curved arrow. For an improper dihedral, each of the two planes that define it is spanned by 3 atoms, with the central atom chemically bonded to the other 2 atoms. We mark each plane by connecting the 2 atoms that are not bonded to each other with a dashed line. The edge shared by the 2 planes is the bond of rotation for the improper dihedral. B. Definition of the C7EQ and C7-AX basins in the phi-psi plane. The heat map is the logarithm of the joint probability p-phi-psi, obtained from a 6s equilibrium molecular dynamics, MD, simulation. For analyses using energy flow and GWF, internal coordinates are the proper choice because they are the natural coordinates for describing protein motions and automatically satisfy all the restraints from the bonded interactions in a protein, figure 3a-b. In contrast, Cartesian coordinates cannot provide useful mechanistic information because their movements are dominated by strong restraint forces from bonded interactions that bear little relevance to the mechanism of protein dynamics. 1D RC is determined by the GWF. Figure 3a shows the GWF for all the proper and improper dihedrals in the system computed with the committor as the projector. The motion of the major RC, phi, is strongly affected by the forces from 4 coordinates, phi itself, the other known RC theta1, and 2 improper dihedrals tau1 and tau2, figure 2a. Interestingly, both tau1 and tau2 are important players in transferring kinetic energy into phi based on our previous analysis of kinetic energy flows in this system. 39. In contrast, double struct W sub phi psi of P sub B is significant, but fancy W sub psi phi of P sub B is small, suggesting that F phi has a significant impact on the motion of psi, but F psi has little influence on the motion of phi. This suggests that the motion of psi is slave to the motion of phi because the latter is the dominant factor for determining F phi. 4041. Consequently, psi, though important for distinguishing the reactant and product states, is not an RC. Figure 3. GWF and generalized work tensor. A. GWF with PB as the projector for all the dihedrals and improper dihedrals in the system. There are 19 times 19 equals 361 lines in the plot. The thick colored lines are integral from phi 0 to phi P sub B of bra F sub I delta, phi ket for Q sub I that has significant magnitude. Corresponding to the blocks with distinct colors in the second column of the generalized work tensor N, C. The rest are colored light gray. B. GWF with phi as the projector. C. 19 times 19 generalized work tensor double struct W of PB, 0 to 0.5, calculated for all the dihedrals and improper dihedrals in the system. Each tensor element is colored based on its value. Figure 4. Committor test and potential energy flow. A. Comparison of the results of committor tests for different RCs. Orange. PDF of PB values of the ensemble of configurations, phi equals 0 degrees and psi equals 40 degrees, with phi as the RC. The same is used in Ref 30. Green. PDF of PB values of the ensemble of configurations, phi equals 0 degrees and theta 1 equals 3.6 degrees, with both phi and theta 1 as the RCs, the same choice as in Refs 30, 31. Blue. PDF of the ensemble of configurations with R sub C equals minus 80.9 degrees. Red. PDF of the ensemble of configurations with R star sub C equals minus 99.5 degrees. B. Potential energy flows through phi, orange, theta 1, blue, tau 1, pink, tau 2, gray, and RC, red. The cyan dashed line represents delta W sub phi plus delta W sub theta 1 plus delta W sub tau 1 plus delta W sub tau 2. Figure 3C shows double struct WP sub B, 0 to 0.5. The generalized work tensor for PB equals 0 to minus 0.5. We included all the dihedrals and improper dihedrals in constructing double struct WPB, 0 to 0.5. Consisting of 19 coordinates in total, we did not include bonds or bond angles in double struct WPB, 0 to 0.5 because terms involving forces from them have high noise. This is because these forces are of high magnitude and oscillate very fast compared to forces from dihedrals. The leading left singular vector of double struct W of PB, 0 to 0.5, is fancy R sub C equals 0.57 theta 1 plus 0.725 plus 0.34 tau 2 minus 0.21 tau 1. To test the accuracy of double struct R sub C, we carried out the standard committor test and compared the performance of C with RCs identified in previous studies. 3, 30, 31, 42. Because RCs must be sufficient for determining PB. Configurations that share the same values of the RCs but differ in other coordinates should all have the same PB value. To test the quality of specific RCs, we harvest an ensemble of configurations that all have the values of the RCs corresponding to the transition state, with the other coordinates randomly sampled. The distribution of PB values for this ensemble should peak around 0.5 if the RCs can determine PB. A narrower distribution indicates higher accuracy of the RCs. Figure 4a shows the results of the committor test. The orange line is the distribution of PB for configurations with phi equals 0 degrees and psi equals 40 degrees, corresponding to the value of phi at the transition state. This distribution peaks at PB equals 0 and PB equals 1, indicating that phi alone cannot determine the committor. The green line is the distribution of PB for configurations with phi equals 0 degrees and theta 1 equals 3.6 degrees. This combination was identified in previous studies as sufficient for determining the committor. 30,31. Indeed, this distribution peaks at PB equals 0.5, though it is rather broad, indicating either missing RCs or the uncertainty inherent in the numerical calculation of PB. 42. This is the limit reached by previous methods, both intuition-guided trial and error and machine learning with the neural network. 30,31. The blue line is the distribution of PB for configurations with double-struck R sub C equals minus 80.9 degrees. It sharply peaks at PB equals 0.5 and has a narrow width, showing the high accuracy of double-struck R sub C. This significant improvement in the accuracy in determining the committor value compared to previous results is due to two factors. 1. The inclusion of two improper dihedrals tau1 and tau2 and 2. The correct coefficients in the analytical expression of R sub C, because the effects of tau1 and tau2 on reaction dynamics are much weaker than those of theta1 and phi, shown by their smaller coefficients in double-struck R sub C. They are much more difficult to detect, explaining why they eluded both human intuitions and machine learning. 30,31. The fact that they are uncovered by double-struck W of PB, 0 to 0.5, demonstrates the capability and precision of the GWF in capturing the essence of dynamics. The red line is the distribution of PB for configurations with double-struck R star sub C equals 0.57 theta 1 plus 0.715 plus 0.34 tau 1 minus 0.21 tau 1 minus 0.1 tau 3 equals minus 99.5 degrees, which is almost identical to the blue line. This suggests that the improper dihedral tau3 is a very minor RC, consistent with its small coefficient in double-struck R star sub C. Moreover, the matrix elements of double-struck W of PB, 0 to 0.5, have inherent numerical uncertainty, especially because PB is numerically evaluated. 3,30,42. The reason that double-struck R star sub C has minimal improvement over C is likely that we have already reached the numerical limit. Thus, double-struck R sub C is likely the optimal 1D RC. Since the GWF determines the rigorous 1D RC, it is likely the correct physical operator for rigorous analysis of protein dynamics in general. Figure 4b shows that delta W sub double-struck R cub C delta W sub phi plus delta W sub theta sub 1, because phi and theta 1 carry the dominant majority of the total potential energy flow through the system based on previous studies. 32,39. This means double-struck R sub C is responsible for the majority of the total potential energy flow through the system, confirming the 1D RC as the single dominant channel for energy flows during a reaction. Is 1D RC curved? An important conceptual question in reaction dynamics is whether the 1D RC is straight or curved. Figure 5. Curvedness of 1D RC. A. The scattered points represent projection of ensembles of configurations with P sub I equals 0.02, 0.3, 0.5, 0.7, 0.9 onto the phi, theta 1 plane. The white straight line through a colored cloud is its linear regressions. Thus, each one represents an approximation to the intersection of the corresponding isocommittor surface with the phi, theta 1 plane. The solid black line is double-struck R sub CPB constructed as a concatenation of 10 short line segments. Each segment is the C for an interval of PB. The double-struck R sub C of PB for a specific PB star is the leading left singular vector of the tensor. Double-struck W of PB, 0 to PB star. To construct the short line segments corresponding to different values of PB, we first prepare 11 ensembles of configurations. Each one contains configurations of a specific PB value. PB equals 0.02, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.9, 0.9, 0.98. Each ensemble of configurations is then projected onto the phi, theta 1 plane, and the center of mass, C sub II equals 1, 2, 11, of each ensemble is computed. The phi coordinate of this series of C sub I defines a sequence of positions along the phi direction. I sub I equals minus 18.9, minus 12.3, minus 7.8, minus 3.9, minus 0.2, 3.3, 7.2, 11.7, 18.4, 24.8 degrees. We start from C1 as the starting point of the first line segment, with its slope as the slope of double struck R sub C of 0.02 projected onto the phi theta 1 plane. The first segment ends at C sub 2 prime, with its phi coordinate equal to phi 2 and its theta 1 coordinate equal to slope double struck R sub C 0.02 middle dot phi 2 minus phi 1. The other segments are constructed in a similar way. The red solid line is constructed in the same manner as the black solid line, but the direction for each line segment is chosen as the direction normal to the linear regression of each PB ensemble. The black dashed line is a straight line in the direction normal to the linear regression of the ensemble of PB equals 0.9. Both solid lines deviate from this straight dashed line, demonstrating the curvedness of the 1D RC. The black and red solid lines are essentially coincidental, showing that double struck R sub C is perpendicular to the iso-committor surfaces throughout the transition region. B. Slopes of the line segments in A as a function of committor. C. Results of committor tests for ensembles of configurations with double struck R sub C PB equals minus 89.0, minus 86.3, minus 83.9, minus 82.6, minus 80.9, minus 79.2, minus 77.5, minus 74.8, minus 71.8 degrees, corresponding to PB equals 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, respectively. There is no physical reason to expect that the 1D RC should be straight, but in practice, it is often assumed so for simplicity. 27,28. This assumption is likely true for small molecules because the barrier top region is very narrow. For complex molecules, this assumption is less warranted due to the extended span of the barrier top. Since alanine dipeptide is the smallest complex molecule, it offers an excellent place to examine this matter. Because the GWF in Figure 3a is nonlinear, the direction of the 1D RC determined by double struck W of PB, 0 to PB star, likely changes with PB, which means the direction of the 1D RC in different intervals of the committor value will be different. Figure 5a, solid black line, shows the projection of the concatenation of 1D RCs for all the intervals of PB onto the phi theta 1 plane, amounting to a piecewise linearization of the true 1D RC. We choose this projection because it is easier to visualize in a plane, and phi and theta 1 are the dominant RCs. Indeed, the 1D RC is slightly curved. This curvilinearity is quantified in Figure 5b, orange line, which shows the slope of the 1D RC as a function of PB. Figure 5c shows the results of the committor test on the curved 1D RC. Indeed, it can predict the committor value with high accuracy over the entire range of PB. To better understand this curvilinearity of the 1D RC, we project it onto the phi theta 1 plane 5 ensembles of configurations. Each ensemble consists of configurations on the isocommittor surface of a specific PB plus or minus delta. The 5 ensembles correspond to PB equals 0.02, 0.3, 0.5, 0.7, 0.9. Delta equals 0.05. It is often assumed that an isocommittor surface is a hyperplane in the configuration space. 27, 28, 35. If this is true, each ensemble of configurations should form a straight strip with a width determined by delta in the phi theta 1 plane. Instead, each ensemble of configurations clusters into an ellipse. To find out the intersections of each isocommittor surface with the phi theta 1 plane, we obtain a straight line through each ellipse by linear regression. Figure 5a, white lines, shows that the direction of these isocommittor lines changes slowly with PB. The red solid curve is the concatenation of the normal directions of all the isocommittor lines. It is slightly bent. Intriguingly, it essentially coincides with the 1DRC, suggesting that the 1DRC, though curved, is always perpendicular to the isocommittor surfaces. New method is robust and cost-effective. In the above results, the GWF was computed using a committor as the projector. Since numerical evaluation of the committor is computationally expensive, 42, it could limit the use of the current method for identifying the 1DRC in large systems. Therefore, we computed the GWF using phi as the projector, which is a good order parameter that can distinguish the reactant and product basins 3 but insufficient for parameterizing the progression of the reaction. Figure 4a. Since RCs control the dynamics of the transition period, not the dynamics within the reactant basin, we consider the range of phi minus 35 degrees, corresponding to the region of PB, 0, 1. Figure 3b shows phi, the GWF calculated with phi as the projector, which differ from double-struck W of PB in Figure 3a. This is expected because the projector significantly affects the ensemble average. Importantly, the 1DRC from double-struck W of phi minus 35 degrees, 0 degrees. Fancy R sub C super phi equals 0.57 theta 1 plus 0.715 plus 0.37 tau 1 minus 0.19 tau 2 is essentially identical to fancy R sub C. Therefore, we can use an order parameter as the projector instead of the committor. This tremendously decreases the computational costs of the current method compared to that of previous methods, 31,36. As now the dominant cost is to harvest a sufficient number of reactive trajectories, which is low compared to the cost of computing the committor. 31,36. Most importantly, substituting PB with an order parameter does not affect the accuracy of the resulting 1DRC. Another important factor is that the number of reactive trajectories required for obtaining the correct 1DRC is much lower than what is required for smooth GWF curves. The results in Figure 3 are averages over 2,000 trajectories, but the 1DRC obtained from averaging over 200 trajectories. Double-struck R sub C of 200 traj equals 0.59 theta 1 plus 0.705 plus 0.32 tau 1 minus 0.24 tau 2 is effectively the same as C obtained from 2,000 trajectories. Moreover, the 1DRC obtained from 100 trajectories is double-struck R sub C of 100 traj equals 0.47 theta 1 plus 0.56 phi plus 0.64 tau 1 minus 0.23 tau 2. Although it does not have the correct coefficients, it does correctly distinguish the four important coordinates, phi, theta 1, tau 2, from the other coordinates in the system, which is what previous methods aimed at and provides highly valuable mechanistic insights. 31,35,36. The reason behind this robustness is probably twofold. One, the GWF tensor is an integration of the GWF curves. Thus, noise in the GWF curves is cancelled out by integration, leading to improved accuracy in the 1DRC. 2. The SVD results are likely constrained by the structure of the GWF tensor and robust to numerical errors. This makes the current approach a robust and cost-effective method for identifying the 1DRC in complex molecules. It is also possible to apply the current method to analyzing existing long-time scale MD simulations of complex conformational dynamics, such as the datasets by D.E. Shaw Research. The major requirement is that the progress of the conformational transition of interest can be characterized by an order parameter selected by the user. This transition can involve more than two stable/metastable states, and the user does not have to correctly identify all the stable states from the beginning. The basic idea can be explained by a schematic example of a two-dimensional system, Figure 6a. In this example, Q1 and Q2 are two RCs, and there are three stable states, S1, S2, and S3, in the Q1, Q2 space. The order parameter alpha can identify S1 and S3 but not S3 from the simulation data and is the projector in GWF calculations. The key is that both the GWF, alpha, and the 1DRC are functions of alpha. Figure 6. Schematic for using the GWF to identify 1DRC for a transition involving three stable states in a two-dimensional system. A. The contour of the potential energy in the Q1, Q2 plane. The three stable states are S1, S2, S3. The red dashed line indicates the order. Parameter alpha. The red arrows indicates the 1DRC for S1 to S2 and S2 to S3 transition respectively. B. The four different elements of double-struct W of alpha. Figure 6b shows the expected features of the four elements of double-struct W of alpha. Because Q1 is the only RC for S1 to S2 transition, only double-struct W sub 11 of alpha has significant magnitude. All the other terms of double-struct W of alpha are vanishingly small because Q1 and Q2 are not coupled in this region, leaving double-struct W sub 12 and fancy W sub 21 essentially zero. And Q2 only undergoes thermal fluctuations, leading to complete cancellations in double-struct W sub 22. The resulting 1DRC will be just Q1. In the S2 to S3 transition, both Q1 and Q2 are RCs, thus all the elements of double-struct W of alpha are significant and the resulting 1DRC is a linear combination of Q1 and Q2. Consequently, we expect to observe a significant change in the direction of the 1DRCs determined in the intervals alpha 1, alpha 2, and alpha 2, alpha 3, respectively, corresponding to the two red arrows in Figure 6a. This kind of change in the 1DRC determined at different values of the projector could be due to hidden stable states in the initial analysis or the intrinsic nonlinearity of 1DRC in complex systems. The actual situation could then be determined by further analysis. In the above discussions, we assume that the simulation data contain a sufficient number of instances of the transition of interest so that the GWF analysis converges. Otherwise, the existing trajectory segments that contain the transition of interest can be used as seeds for TPS to proliferate more reactive trajectories. Discussion. In this paper, we developed a general mechanical operator, the GWF, that can help to answer some fundamental questions in protein dynamics. Collectivity in functional protein dynamics. Functional protein dynamics often involve significant changes in the global protein structure, which are assumed to be controlled by collective modes. However, it remains a puzzle what these collective modes are and what their physical origin is. A global conformational change results from the aggregation of many local movements. Each local movement is described by an internal coordinate. Individual local movements are mechanically coupled together by the double-struct S tensor. Thus they are synergized with each other, forming collective modes. Understanding the collectivity in conformational dynamics requires understanding what this synergy is and what determines it. The GWF encapsulates the effects of the couplings induced by the double-struct S tensor. Its left singular vectors are the collective mode responsible for the global conformational change. The coefficients of these singular vectors define the synergy between different internal coordinates. For example, in double-struct are star sub c, phi, theta 1, and tau 1 correlate with each other but anti-correlate with tau 2 and tau 3. The GWF is the physical determinant of this synergy and the collectivity of protein dynamics. Tentative roadmap for the structure minus function. Relationship of proteins. A critical link between the structure and the function of a protein is its functional dynamics, which is controlled by the RCs. The RCs are determined by the GWF, which summarizes how the forces in the protein impact the motions of the coordinates that are extensively coupled together by the double-struct S tensor. Both the forces and the double-struct S tensor are determined by the protein structure. Summing these factors up leads to a tentative roadmap for the structure minus function relationship. Figure 1b. The structure of a protein determines both atom minus atom interactions and the double-struct S tensor. Together, they determine the GWF, which determines the dominant forces in the protein and the RCs. The RCs control the functional dynamics, which determines the protein function. Finally, the GWF provides a rigorous and computationally efficient method for identifying the 1D RC for a single-channel reaction. For the C7EQ to C7-AX isomerization of an alanine dipeptide in vacuum, we obtained the piecewise linearization of the true 1D RC over the entire transition region, which showed that the 1D RC is slightly curved. The curved 1D RC can predict the committor value with an accuracy far exceeding what was achieved before by both human intuitions and machine learning, attesting the value of the rigorous physics-based method. Most importantly, the 1D RC is determined by a general mechanical operator, without resorting to any informatics approach or human intuitions. Methods. All simulations were performed using the MD software suite Grail Max 43 with transition path sampling implemented. Amber 94 force field was used to facilitate comparison with previous results. 30, 30. 2, 39, 44, 45. The structure of the alanine dipeptide was minimized using the steepest descent algorithm and heated to 300 K using velocity rescaling with the coupling constant of 0.2 Ps. The system was then equilibrated for 200 Ps, and no constraints were applied. The time step of integration was 1 Fs. Basin C7EQ is defined as -190 degrees less than phi, -55 degrees and -60 degrees less than psi less than 190 degrees. Basin C7-AX is defined as 50 degrees less than phi less than 100 degrees and -80 degrees less than psi less than 0 degrees. We use the transition path sampling method to generate the ensemble of reactive trajectories between these two basins that are used in all the analysis discussed here. 3. All the average quantities discussed in the text were averaged over 2,000 trajectories. Author information. Corresponding author. Alma Richard Lone and Hill Department of Biomedical Engineering, the University of Illinois at Chicago. Chicago, Illinois 60607. United States, ORCID.org/00000029872 to 7333, phone 312-996-7225, email oma@uic.edu. Authors: Shan Wu Richard Lone and Hill Department of Biomedical Engineering, the University of Illinois at Chicago. Chicago, Illinois 60607, United States. Huey Lee Richard Lone and Hill Department of Biomedical Engineering, the University of Illinois at Chicago. Chicago, Illinois 60607, United States. Complete contact information is available at https://pubs.ax.org/10.1021/ax.jctc.2C00132. Notes. The authors declare no competing financial interest. Acknowledgements. We thank the National Science Foundation for Financial Support, Award, CHE 1,665,104, and the anonymous reviewer for the excellent suggestions that help to improve the manuscript. References. 1. Frauenfelder, H., Sliger, S.G., Woolens, P.G., The Energy Landscapes and Motions of Proteins. Science 1991, 254, 1598-1603. 2. Hensler-Wildman, K. Kern, D. Dynamic Personalities of Proteins. Nature 2007, 450, 964-972. 3. Beaulieu, P. G. Chandler, D. Delago, C. Geisler, P. L. Transition Path Sampling, Throwing Ropes Over Rough Mountain Passes in the Dark. Anu. Reverend Fiss, Chem. 2002, 53, 291-318. 4. Kramers, H. A Brownian Motion in a Field of Force and the Diffusion Model of Chemical Reactions. Physica 1940, 7, 284-304. 5. Grote, R. F. Hines, J. T. The stable states picture of chemical reactions. Point 2. Rate constants for condensed and gas phase reaction models. J. Chim, Phys. 1980, 73, 2715-2732. 6. Wigner, E. The transition state method, trans. Faraday Sock. 1938, 34, 29-41. 7. Henge, P. Tauchner, P. Borkovic, M. Reaction rate theory, 50 years after Kramer's. Reverend Maud. Fies. 1990, 62, 251-341. 8. Byrne, B. J. Borkovic, M. Straub, J. E. Classical and Modern Methods in Reaction Rate Theory. J. Fies. Chim. 1988, 92, 3711-3725. 9. Chandler, D. Statistical Mechanics of Isomerization Dynamics in Liquids in Transition State Approximation. J. Chim, Phys. 1978, 68. 2959-2970. 10. Pechukis, P. Statistical Approximations in Collision Theory, in Dynamics of Molecular Collisions Part B, Miller, W. H. ed. Plinum. New York, 1976. Volume 2, p. 269. 11. Barjaksai, A. Bussi, G. Parinello, M. Well-tempered. Metadynamics, a smoothly converging and tunable free energy method. Fies. Reverend Lett, 2008, 100, number 020603. 12. Darv, E. Rodriguez Gomez, D. Pohorial, A. Adaptive biasing. Force method for scalar and vector free energy calculations. J. Chim, Fies. 2008, 128, 144,120. 13. Hammelberg, D. Mongan, J. McCammon, J. A. Accelerated Molecular Dynamics, a promising and efficient simulation method for biomolecules. J. Chim, Phys. 2004, 120, 11,919-11,929. 14. Invernizzi, M. Piaggi, P.M. Parinello, M. Unified Approach to Enhance Sampling. Fees. Reverend X 2020, 10, number 041034. 15. Kong, X. J. Brooks, C. L. Lambda Dynamics, a New Approach to Free Energy Calculations. J. Chim, Phys. 1996, 105, 2414-2423. 16. Lio, A. Parinello, M. Escaping Free Energy Minima, Proc. National ACAD, Sci. U. S. A. 2002, 99, 12,562-12,566. 17. Valson, O. Tiwari, P. Parinello, M. Enhancing Important Fluctuations, Rare Events and Metadynamics from a Conceptual Viewpoint. Anu, Reverend Phys. Chim. 2016, 67, 159-184. 18. Zhang, L. Q. Chen, M. G. Yang, W. Random walk-in. Orthogonal space to achieve efficient free energy simulation of complex systems. Proc. National ACAD, Sci. U. S. A. 2008, 105, 20,227 - 20,232. 19. Zheng, L. Q. Chen, M. G. Yang, W. Simultaneous escaping of explicit and hidden free energy barriers, application of the orthogonal space random walk strategy and generalized ensemble-based conformational sampling. J. Chim, Phys. 2009, 130, 234,105. 20. Zhang, L, Q, Yang, W. Practically efficient and robust free energy calculations, double integration orthogonal space tempering, J. Chim, Theory Compute, 2012, 810-823, 21, Du, R, Pandy, V, S, Grossberg, A, Y, Tanaka, T, Sheknovich. ES on the transition coordinate for protein folding, J. Chim, Phys. 1998, 108, 334-350, 22, Writer, D, on the eigenfunctions of the Fokker-Planck operator, and of its adjoint, Physica A 1987, 142, 103-121, 23, Onsager, L. Initial recombination of ions, Feis, Revre, 1938, 54. 554-557, 24, Wang, Y, Ribeiro, J, M, L, Tiwari, P. Past future information. Bottleneck for sampling molecular reaction coordinate simultaneously. With thermodynamics and kinetics. Nat. Commune. 2019, 10, 3573, 25, Mart, A, Pasquale, L, Wu, H, Noe, F. Vampnitz for deep learning of molecular kinetics. Nat. Commune. 2018, 9, 5, 26, Langer, J. S. Statistical Theory of the Decay of Metastable States Ann. Phys. 1969, 54, 258-275, 27, Bereshkovsky, A. Szabo, a one-dimensional reaction. Coordinates for diffusive activated rate processes in many dimensions. J. Chim, Phys. 2005, 122, number 014503, 28, Ma, A, Nag, A, Dinner, A, R. Dynamic coupling between coordinates and a model for biomolecular isomerization. J. Chim, Phys. 2006, 124, 144,911, 29, Bereshkovsky, A. M., Szabo, A. Diffusion along the splitting slash. Commitment probability reaction coordinate, J. Phys. Chim, B. 2013, 117, 13,115-13,119, 30, Boluis, P. G. Delago, C. Chandler, D. Reaction coordinates of biomolecular isomerization, Proc. National, ACAD, Sci. U. S. A. 2000, 97, 5,877-5,882, 31, Ma, A. Dinner, A. R. Automatic method for identifying reaction coordinates in complex systems. J. Phys. Chim, B. 2005, 109, 6,769-6,779, 32, Lee, W. Ma, A. Reaction mechanism and reaction coordinates. From the viewpoint of energy flow, J. Chim, Phys. 2016, 144, 114,103, 33, Keetman, S. L. Schwartz, S. D. Reaction coordinate of an enzymatic reaction revealed by transition path sampling, Proc. National ACAD, Sci. U. S. A. 2007, 104, 12,253-12,258, 34, Frasick, M. Arjun, A. Boluis, P. G. An extended autoencoder. Model for reaction coordinate discovery in rare event molecular dynamics datasets. J. Chim, Phys. 2021, 155, number 064103, 35, Antonio, D. Reaction coordinate for complex systems. J. Chim, Phys. 2009, 130, 151,103, 36, Peters, B. Trout, B. L. Obtaining reaction coordinates by likelihood maximization, J. Chim, Phys. 2006, 125, number 054108, 37, Lee, W. Ma, A Recent Developments in Methods for Identifying Reaction Coordinates. Mol, CMOL, 2014, 40, 784-793, 38, Noe, F, Olson, S, Cooler, J, Wu, H. Boltzmann generators. Sampling equilibrium states of many body systems with deep learning. Science 2019, 365, DOI 10.1126/science.AAW1147, 39, Lee, H. Ma, A Kinetic Energy Flows and Activated Dynamics of Biomolecules, J. Chim, Phys. 2020, 153, number 094109, 40, Frauenfelder, H. Chen, G. Berenson, J. Finnemore, P. W. Jansen, H. McMahon, B. H. Strew, I. R. Swenson, J. Young, R. D. A Unified Model of Protein Dynamics, Proc. National, ACAD, Sci. U. S. A 2009, 106, 5129-5134, 41, Frauenfelder, H. Finnemore, P. W. Chen, G. McMahon, B. H. Protein folding is slave to solvent motions, Proc. National, ACAD, Sci. U. S. A. 2006, 103, 15,469-15,472, 42, Delago, C. Volues, P. G. Geisler, P. L. Transition path. Sampling. Adverb Chim, Phys. 2002, 123, 1-78, 43, Hess, B. Kutzner, C. Vanderspoel, D. Lindahl, E. Gromax 4, Algorithms for Highly Efficient, Load-Balanced, and Scalable Molecular Simulation, J. Chim, Theory Compute, 2008, 4, 435-447, 44, Case, D. A. Perlman, D. A. Caldwell, J. W. Cheatham, 3, T. E. Ross, W. S. Simmerling, C. L. Darden, T. A. Mers, K. M. Stanton, R. V. Cheng, A. L. Amber 5.0, University of California, San Francisco, 1997, 45, Perlman, D. A. Case, D. A. Caldwell, J. W. Ross, W. S. Cheatham, T. E. D. Bolt, S. Ferguson, D. Sable, G. Coleman, P. Amber, A Package of Computer Programs for Applying Molecular Mechanics, Normal Mode Analysis, Molecular Dynamics, and Free Energy Calculations to Simulate the Structural and Energetic Properties of Molecules, Compute, Phys. Commune, 1995, 91, 1-41.